The topic of our group is finite element analysis on car lower control arm, and now I am going to introduce about it. Car lower control arm is one of the core structures in the front suspension system. It connects the wheel hub and steering cunker to the frame of the vehicle. It also allows wheel to move up and down while preventing forward and rearward movement. However, it can be damaged easily due to corrosion, collisions, hard wheel impacts, and many more, which will negatively impact handling, comfort, and safety. There are several types of damage that can occur on it, such as frame damage and bushing damage. Frame damage is our focus, which is due to over-limit force add on it.
So hello and hi, my name is Umar Zaki and I will continue with the problem solving process of this study. So for assumptions, there are many assumptions that will be applied on the study to allow simplification of the calculation and the simulation. For example, we will set the weight of the car around 2000 kilograms and the car will achieve around 50-50 weight distribution along its front and back axle. Furthermore, the weight transfer is neglected in the study, so we can say that for each of the lower control arm will only support around 500 kilograms from the car. And other than that, we will assume that the car will have a linear relationship with time in its acceleration and deceleration aspect, although this might not be true for a real car. Other than that, we will assume that all 4 tires will use the same suspension geometry and all of the components of the lower control arm is undeformable. Other than that, we will assume that the force that exerted by the tires are solely handled by the lower control arm. So this will be the model that we will use for the study, and this will be its dimension, and the force that will be exerted on the lower control arm is on its knuckle. So case 1 will be when the car is accelerating, so we will use a BMW 5 Series as our model. So from the BMW website, it is told that the car can achieve 0 to 100 km an hour in around 6 seconds. So by using a simple motion equation, we can find out that it can exert around 0.48 Gs during acceleration, and using the FMA equation, we can find out that it will exert around 2354 newtons on the lower control arm on its knuckle. So for boundary conditions, we will set fixed geometry on the rear and front bushings, and the material that will be used for the lower control arm is IC 1023. So this is the properties and its value that will be used during simulation. So we will proceed with the results discussion produced by the simulation. So this is the model, is in the SolidWorks. So I will run the study. So as shown here, the boundary conditions are set in the rear bushings and in the front bushings. So the force will be applied around here at the knuckle. So this will be the model after the simulation is run. As shown here, it is the form, and this is the von Mises plot. So from the plot, it can be seen that most of the lower control arm is lower than the maximum stress, and the maximum stress occurs around here at the joint between the knuckle, and it occurs around 80 megapascals. For displacement chart, as shown here, so the maximum displacement that will be occur in the lower control arm at the accelerating condition is around 0.116 millimeters, which is small considering for the movement of the lower control arm in vertical direction. So the lower control arm may not deform very much during acceleration. So the factor of safety, as shown here in the chart, I have set the factor of safety in the upper limit of 10. So most of the lower control arm achieve the factor of safety around 10 or above. However, there are some areas that have a factor of safety around 6 or below that. So for example, around the bushings here, it is plotted in green, and for the lowest factor of safety that occur is in the same location as the maximum stress that occurred in this inside of the knuckle around this location, which have a factor of safety around 3.1. This shows that the lower control arm are still in the safe region of operating. However, it should be considered that the assumptions that are set for this study is very lenient for this lower control arm. So in real situation where conditions such as weight transfer and the lower control arm maybe not in perfect conditions, This factor of safety may be too low for the lower control arms. Thus, for this location, a reinforcement must be needed, such as making the knuckle more thicker, or like make the lower control arm from a stronger material. So for the mesh convergence study, it is shown in the chart. We have compared the results as the mesh size becomes smaller. So we have done 3 different mesh sizes, which is 2, 5, and 10 millimeters. As shown in the graph, the smaller the mesh size, the higher the displacement and the stress. However, it should be noted that the trend line for the stress and displacement curve differently. For displacement, the curve downwards. However, for the stress, it curve upwards. This means that the benefit of having a smaller mesh size may be not that great for displacement. As we all know that smaller mesh size, we use higher computational power, and for our case, our computational power is limited to mesh size of 2 millimeters. However, for stress, it is shown the curve upwards, so it might be beneficial to run this study in smaller mesh size, as we can know how high the stress can occur in the lower control arm. As the smaller the mesh size, the more accurate the results can be.
Hi, my name is Asreen Dzaqwan bin Muhammad Safuri. I am from section 1. Now, I would like to explain another most critical loading case for lower control arm, which is occur when a car is decelerating or braking. Why we need to consider this load case? Well, today's many people have their car and they will use it to move, and of course they will also decelerate their car and experience the braking condition. This load case actually indicates the real situation of what we face every day. We can also see the force analysis towards the lower control arm, especially when braking load is applied. Lastly, this load case is significant because it helps us to determine which part of the lower arm that experience the most critical part. Note that few assumptions also is made for this project, and one of them are the weight transfers will be neglected. The car achieve a perfect 50-50 weight distribution among its both front and back axle. Bushings cannot be deformed. Braking exhibits a linear relationship with time, and damping effect is excluded. And most of the assumption is quite similar with load case 1. And note that these assumptions is made only for this project, and for the real life situation, it will produce different results. For the calculation, first we need to consider the boundary conditions, which is both of the bushings of the lower control arm are fixed support. This simply means that the damping effect is not occur because we assume the bushings are rigid. For the force involved in this load case is actually due to the braking force that occur at the knuckle of the lower control arm. For the mass of the car supported by each sway bar, we obtain from mass of the car at 2000 kilo divided by 4, and we obtain the mass is 500 kilogram. And note that this braking case, the vehicle decelerates or simply called braking with a constant 0.94 Gs, and we can see the G force applied when the car is braking is much more greater than the G force when the car is accelerating in load case 1. For the force, we simply calculate from the formula force equal to MA, and we obtain it. The value is 4610.7 Newton. Next, we can also obtain the simulation results from the SolidWorks simulation, and basically this simulation will provide us the von Mises stress and also the displacement results. As we can see from the table, the maximum von Mises stress is occur at 91.04 MPa, and this stress is not exceeding the yield strength of this material, which is just 248 MPa, and therefore we can consider it is safe. From the simulation also, we can see the most critical part is occur at the front bushing. This is true because when a car is braking, the force or simply or the braking force will be applied on the opposite direction, and of course the front part will be the most critical part. Next, we also obtain the displacement, and as we can see the value is quite small, which is just 0.0969 millimeter, and since the displacement is very small, there will be no significant effect towards the suspension system throttling. We also do the mesh study of this load case. As we can see, this graph shows the relationship of volumetric stress and displacement in different mesh size. Note that in the mesh size used is from the fine to coarse size, or to be precise, it is 2, 5 and 10 millimeter. It clearly shows that from the graph, a finer mesh will evaluate greater stress, and this depicts that a fine mesh might represent the local stress concentration patterns in a zone close to the load application. That's why a fine mesh is always chosen for the analysis. Besides, from the graph also we can see that when the smaller mesh size is used, the greater the maximum stress and displacement. Hence, a fine mesh provides more accurate results for this case. Lastly, we obtain the factor of safety for the lower control arm when the car is braking. As we can see from the table, the minimum value of the factor safety is 2.7, and since this value is greater than 1, it is considered safe for this lower control arm design. But for the real case situation, the factor of safety should be more greater, because to ensure better optimization of the lower control arm design and to make sure it is safe to use. Usually during critical conditions, especially when we brake the car suddenly, the most affected part must be strong enough, and that's why we need to use the greater factor of safety of the material. And besides that, we can also see the most critical part will be at the bushings of the lower control arm.
In conclusion, from the analysis of both load cases, none of them will have the risk to fail, as the safety factor is good enough for all situations. However, the most critical case is during braking of the vehicle. In this case, the maximum stress add on it is 91.04 megapascal at the front bushing, and the maximum deflection is 0.0969 mm at the outermost of the cone curve. From this case, its safety factor is 2.7, which is lower than the safety factor of case of accelerating, which has safety factor of 3.1. However, the result shown is not fully true in real life, due to weight transfer was being neglected, which caused much less stress will be acting on it in our case study compared to real life situation. There is possibility for the stress caused by weight transfer to cause it to fail in real life. So more tests are required to be carried out in real life to ensure it works safely. It is important as it may endanger the drivers and passengers' life once it fails.